We'll now have the final talk of the meeting. Tudor Dimofte will be finishing his mini course on higher structures in SUSY QFTs. Yeah.
Thanks. And since it is the last talk of the conference, I think it falls on me to ask everyone to join me in thanking the organizers and especially Aswin for an awesome 2 weeks. This is a fantastic program. Thanks. Right, so I wanted to finish up some things from last time and maybe say some things about 3D n equals 4 theories. We talked about G actions in quantum mechanics and got to a statement that the Hilbert space in quantum mechanics with a flavor symmetry was an A infinity module for the homology of G, and the Hilbert space in quantum mechanics with the G gauge symmetry was a module for the G equivariant cohomology of a point. And so this is where the gamma operations came in, and this is where polynomials in sigma showed up. And I could have thrown A infinity on this side as well, but that structure doesn't do anything interesting there. Whereas it is interesting there. Right, so I first want to address why we might care about this. Especially sort of this, on these gamma operations on the flavor side. There are a few reasons. One, sort of abstractly, is that the existence of this module structure restricts the allowed deformations of the quantum mechanics. Specifically restricts deformations that preserve a G action. Examples of deformations include, changing the metric of your target, introducing a Morse function in the form of a real superpotential, and so on. So whatever you do to the theory has to keep the full module structure of the supersymmetric Hilbert space. So you could have, say, two different theories that have this, that look like they have the same supersymmetric Hilbert space, and you might want to ask, are those actually related by some supersymmetric deformation that preserves the G action, and that can only happen if the full module structure is the same. So that's sort of abstract. It does, in some cases, tell you very quickly that there can't exist a G-invariant Morse function. Another slightly cooler feature of this is that the module structures wait. Sorry, can you ask that again in what context? Yes, so a Morse function localizes everything to points, and it kills any gamma operations. So like for S3, there is a Morse function, but there's no U1 invariant Morse function because it would kill all the gamma operations. Right. So the module structures control gauging and ungauging. Sorry? No. It's if the U1 is Hamiltonian, then all the gamma operations vanish. Equivariant cohomology is formal, and there exists a Morse function just coming from the Hamiltonian. So no, I genuinely mean any Morse function. And for a U1 action on the hop vibration, that's not a Hamiltonian action. Space is not symplectic. So I really just mean Morse functions. Deformations of the theory by a real superpotential. Right. So module structures control. Sorry. The mathematical statement behind that, the Gorski-Kottwitz-McPherson statement, is that there's actually an equivalence of categories between homology of G, A infinity modules, and cohomology of a point modules, where everything is graded, and there's some particular finiteness conditions that need to be stuck on. There are functors going back and forth, which physically mean there are ways, there should be a way to gauge and ungauge the Hilbert space as long as you know the module actions. And going one way is slightly more intuitive, so I want to describe that. So how do we gauge? So we want to go from cohomology of X to equivariant cohomology of X. Well, what are we supposed to do? We tensor this thing with polynomials in sigma, take invariance, and deform the differential. Now, this deformed differential, acting on invariant forms, is really D plus the gamma operation, because acting on invariant forms, IV and gamma are the same thing. So gauging means deforming the differential by gamma. And deforming a differential initiates a spectral sequence. So one can do this perturbatively. And compute the G-equivariant cohomology of X by starting with the cohomology of X as a gamma module, taking cohomology of that with respect to sigma times the gamma operation, taking cohomology of that with respect to sigma squared times the higher gamma operation, if it exists, taking cohomology of that with sigma cubed times the next higher gamma operation, and so on. And let me remind you what the higher gamma operations were. Yes. Yes. Yeah, these are the pages. Yeah, I know, but but I actually find this a rather more efficient way to think about it. Right. So just as a reminder, gamma 2 was gamma the inverse, gamma, and so on. Yes. The what? No. I mean, it stops at some point. Probably because this is, well, certainly because this is simpler than the general case, but I can't tell you exactly why right now. So the A infinity operations on the A infinity operations on the Hilbert space in the flavor theory tell you exactly how to gauge the thing and get equivariant cohomology. Going back is also interesting, and I think I actually want to tell you about it in terms of two-dimensional boundary conditions rather than giving you the map immediately. Okay. One last nice application is that the spectral sequence procedure gives us a rather nice way to think about supersymmetry breaking. There's a third option sitting halfway between flavor symmetry and gauge symmetry. There's this thing called introducing a twisted mass. So given the theory with global or flavor G symmetry, one can introduce or deform by M sitting in the complex Cartan of the Lie algebra. It's called a twisted mass. This is, so deforming by M amounts to introducing a superconnection that's constant. So M belongs to a constant superconnection. Where the connection part is just 0, but we're allowed to turn on just a constant value of one of the other fields. The Hilbert space in the presence of the twisted mass, the supersymmetric Hilbert space, is exactly what you would get from the gauged theory, where M were this dynamical field sigma, with sigma set to a constant. It's a mathematically, it's a localization of the equivariant cohomology at a non-zero value of sigma. So now m is just a number. Now, why is this interesting? If we have a free action, of G on X, the supersymmetric Hilbert space in the presence of a mass deformation will be empty. There won't be any supersymmetric ground states. There are a few ways to see that. So the equivariant cohomology is just cohomology of X mod G, which is finite dimensional. So in particular, as a C of sigma module, sigma to some power has to be equal to 0. It's not a free module. And turning on a mass forces sigma to not be 0. So we're taking a module in which sigma to some power is equal to 0 and localizing it at a point where sigma is not 0, and the entire thing vanishes. So, right. From a more physicsy point of view, introducing this twisted mass deforms the action, or deforms the Lagrangian, by a term that looks like m times the vector field generating the G symmetry squared. And if the action is free, this vector field never vanishes. So there's just a term of order m squared added to the classical energy. There shouldn't be any supersymmetric ground states. OK. Now, the thing that's cool about this is that we have the spectral sequence gives us some control over the ground state energy. So question, what's the energy of the ground state? I.e., the lowest eigenvalue of the m-deformed Hamiltonian. So the Hamiltonian used to be the form Laplacian as an anti-commutator of d and d dagger. Now it's an anti-commutator of d plus miv, d dagger plus m bar, iv dagger. It's been deformed at quadratic order in m. So the question is, what's the lowest eigenvalue if it's not 0? And a simple result by us, a generalization of the Hodge theorem, is that if sigma to the n is not 0 in equivariant cohomology for some n, another way to say that is if the spectral sequence doesn't die after n steps, if it's still going, then the ground state energy is at least of order m to the 2n plus 2. So if you think of m as a very small deformation, we deform the Lagrangian at second order in m. Nevertheless, the quantum ground state energy can be much, much, much higher if it takes a long time to kill the cohomology. I mean, maybe a slightly silly way, what's cool about that is that it has a flavor of the cosmological constant problem. Yes? Yeah, M's in the same multiplet. Dynamically. So it lifts the vacuum energy. It breaks supersymmetry in the vacuum. By the classical contribution. Yeah. Yeah, absolutely. Yeah. Yeah, which is what's cool and surprising about this. So there are cancellations. If you run perturbation theory for the corrected energy, there are cancellations to all orders up to the point where the spectral sequence converges. So like the first n orders roughly in perturbation theory vanish. Let me. And these cancellations are topological. So again, they're independent on deformations of the theory as long as those deformations preserve the G action. Let me give you examples. It's actually really easy to engineer x's for which n is arbitrarily large. So for U1 action on S1, well, here the equivariant cohomology is, well, it kills sigma at first order, so nothing special happens. The ground state energy in the mass deformed theory is of order m squared. But then we had this action on the hop vibration. And for the hop vibration, sigma is killed at quadratic order. And now there's a miraculous cancellation. The energy is of order m to the fourth. And of course, one needs some other parameter in here. That's the radius of the S3. Hop vibrations generalize. So S, any odd sphere has a hop vibration over complex projective space. And one can run the same calculation. So rotating the hop fibers is a free action. U1 rotating the fibers of S17 gives equivariant cohomology. I think looks like C of sigma mod sigma to the ninth. And the ground state energy looks like is of order m to the 18th. Right. I sort of doubt at the moment that this is of any phenomenological use, but it's kind of a cool mechanism to get at least power law suppressed ground state energies. Okay, so that's why we care. Now let me lift the entire story to 2 dimensions. Sorry? No, it's exactly the opposite. So So sorry, we need the G action to be free, and the module is very much not free. No. The condition that is that module. So I mean that the module is finite dimensional. So the module is fully torsion, I guess. So sigma to some power dies. So that's the opposite of the equivariantly formal case, where the G action, at least topologically, looks like it's trivial, and the module is free over the polynomial algebra. So you get polynomials of all orders in sigma. Yes. Yes. Well, not just free, but it's a little more. It's not just an arbitrary free module, but it's just the cohomology of X. It's times C sigma. That's equivariantly formal. That implies that you will preserve supersymmetry under a mass deformation. I think you can ask for less than that and still preserve supersymmetry. But yeah, sorry, forget equivariantly formal. I think you're right. If you just have a free module, then you will, yeah. You need the localization. You need to, if you take this equivariant cohomology and you set sigma to a number, you need that to still be a non-vanishing, non-zero vector space. Because there are excited states entering in. And it is definitely a loop effect. Yeah. Yes, because the energy of the excited states is just right to cancel h-bar corrections to the energy of the classical ground states. Yeah. Maybe, sorry, yeah, sure. So that this doesn't look quite so magical. I should also point out that if without turning on the mass in these large sphere theories, there are two supersymmetric ground states. Like on S17, there are two supersymmetric states of fermion number 0 and 17. And the Hamiltonian can only change fermion number by 1, by plus or minus 1. The mass deformed Hamiltonian. And so in order to, these states have to talk to each other in order to cancel out, in order to lift from in order to lift their energies, and that takes you have to go to very high order in perturbation theory to get them to communicate. Okay, I'll go on. Yes. Yeah, well, so the proof involves translating between algebra and geometry, right? So one needs to try to diagonalize perturbatively this deformed Laplacian, and you see the correspondence very directly. Okay. This story all has a nice a nice explanation in 2 dimensions. So I want to consider the A-twist of 2D 2,2 G-gauge theory. This theory has a category of boundary conditions. I'll just call boundary, which is the thing that morally should be thought of as the Fukaya category of point mod G. But I'm going to construct this category. There are 2 sort of distinguished elements in the category of boundary conditions that just come from supersymmetrized Neumann and Dirichlet boundary conditions. So 2 elements, 2 objects. There's Neumann, that as a classical boundary condition for fields sets the curvature at the boundary equal to 0. This preserves G-gauge symmetry on the boundary, in the sense that we still have gauge transformations acting along the boundary as symmetries, and we quotient out by those. There's no, I just wrote Neumann, or of F. Oh, I should just write F. In 2 dimensions, it doesn't matter. And then there's Dirichlet. Which sets the component of the connection parallel to the boundary to 0. And this manifestly breaks G-gauge symmetries. The only gauge symmetries that preserve this strength are constant ones along the boundary. So this comes with a global, in other words, constant G symmetry on the boundary. Constant. Okay. Now, a bunch of other objects can be obtained by taking any Riemannian manifold with the G symmetry and coupling it to Neumann. So we put a Neumann boundary condition on a half space that has a G-gauge symmetry. And these are going to be physics words. We take a copy of quantum mechanics to X that has a G global symmetry and use the connection, use the superconnection on the boundary to gauge the G global symmetry in the quantum mechanics. So gauge. And I will just write this boundary condition as X. So our category has a bunch of objects labeled by Riemannian manifolds with G symmetry. In fact, even Neumann and Dirichlet can be understood as Riemannian manifolds with G symmetry. In this language, Neumann itself is just a point. Coupled to trivial quantum mechanics, I get Neumann back. Dirichlet is equivalent to G. And that may not be an obvious statement. Yes. It is only a vector multiplet. It's pure. Yes. Sorry? Yeah, but they're enforced by supersymmetry. So preserving A-type supersymmetry tells you what to do with sigma. The Neumann boundary condition sets the normal derivative of sigma to 0, and the Dirichlet boundary condition kills sigma. There's no. There is. We'll find it in a second, but it's weird because it comes from. They're boundary values of, well, it comes from colliding fermionic vortex operators with the boundary physically. But we'll do some math magic and find it in a second. All right. So it feels like we're sort of in a different seminar. So labeling objects of this category by Riemannian manifolds. The Neumann boundary condition is actually just a point. P is a point. And the Dirichlet boundary condition is G, and I didn't explain that. So G has G as a manifold has two G actions on the left and the right. I can use one of them to couple to the bulk. And I'm left with the other one as a global symmetry. That's one indication that this identification is reasonable. Another one will come from starting to compute some Hums. Another way to think about this is in higher dimensions, I would use the word spontaneous symmetry breaking. Throwing a copy of G as matter into a G gauge theory kills the G symmetry completely, which is what a Dirichlet boundary condition is supposed to do. The stabilizer of any point on G under the left action is trivial. Yes. I'm coupling it to the boundary, yes. And using it to define a boundary condition. I mean, this is in quotes for the moment. I can answer that a little bit better later on, but I'm just going to construct the category boundary conditions. Does it have? No. Yeah, I mean, we're in one dimension. Yeah, right. The boundary is one-dimensional, so funny things might happen with discrete symmetries, but this will be fine. Yes, if you build a Dirichlet sandwich, you can see this copy of G. No. I mean that's matter fields. It's not sigma or gamma or any of the things you've met. I mean, it's just whatever you would use in quantum mechanics. G is X, right? I'm treating G as an example of X. Yeah, I'll get there. Okay, so second. Okay. Let me describe the HOMs. So there are two ways to understand HOM of xy. It's either the space of local operators sitting at a junction of x and y boundary conditions, or as a vector space, it's the space of states. Between x, it's the space of states on a strip sandwiched by x and y. In formal TQFT language, it's z of an interval with x and y boundary conditions. Also, I'm changing orientations and implicitly using Hodge duality all over the place, and I don't want to say anything about it. Okay. Given that physical sort of definition of HOMs, we can actually compute them. So what happens if we sandwich the two-dimensional gauge theory between x and y boundary conditions? We'll get quantum mechanics in one dimension whose target is x times y with a G gauge symmetry acting diagonally on the product. So this HOM space is the Hilbert space in gauged quantum mechanics to x times y. In other words, it's G-equivariant cohomology of x times y. And that is enough to run the entire story. What is the rest of the story? By forming sandwiches with Neumann and Dirichlet, we can recover gauged and ungauged quantum mechanics. A sandwich with Neumann gives you the one-dimensional gauged X theory. And we can simply check that the Hilbert space is correct. So this one-dimensional Hilbert space is going to be HOM Neumann X. In other words, that's HOM point X, which is equivariant cohomology of point times X, which is equivariant cohomology of X, which is the right answer. Similarly, if we want to recover just the flavor symmetry quantum mechanics, we sandwich with Dirichlet. That gives pure ungauged quantum mechanics on X, and the Hilbert space is HOM Dirichlet X. In other words, G-equivariant cohomology of G times X, because Dirichlet was G. And now the G action is free, and we can kill a factor of G. That's just ordinary cohomology of X. And this is, for me, I think the most sensible way to see that that the Dirichlet boundary condition given sort of semi-classically like this is equivalent to to coupling to a copy of G. It does the right thing in the sense of recovering ungauged quantum mechanics. Okay, but a nice thing about both of these pictures is that they end up resolving the module structures I talked about earlier. Even a simple version of that can be seen in the Dirichlet X sandwich. So in X quantum mechanics, there's a global symmetry. On the strip, the global symmetry is not evident on the X boundary. The global symmetry is acting on the D boundary. Yeah, I mean, it's Neumann coupled to X. The other thing you have sitting on these boundary conditions are algebras of local operators that are totally canonical, because N and D are totally canonical. And it turns out that N contains the sigma algebra, whereas D has the gammas. Let's check that abstractly. So the endomorphisms of N, in other words, Ham from N to itself, is computed as G-equivariant cohomology of point cross point. In other words, G-equivariant cohomology of the point, which is the sigma algebra. Or in terms of field theory, what you want to say is that there was a sigma field in the bulk, and the Neumann boundary condition preserves the boundary value of that sigma field, and so we get local operators on that boundary. Similarly, the endomorphism algebra of the Dirichlet boundary condition is Ham dd. It's G-equivariant cohomology of G times G. And we can use the G action freely to kill one of the factors. That's cohomology of G, and like I said, I sort of need to Hodge dualize freely to say this efficiently. That's the homology of G algebra. So this is the gamma algebra. Now, I'll get back to the statement about where the gamma operators come from. They do, in fact, happen to come from bulk operators here as well. They didn't need to, but it does so happen that 2D pure gauge theory has both sigmas and gammas in the bulk. The gammas in the bulk are slightly non-trivial. They're formed out of gauginos, but the gauginos themselves are not in Q cohomology, and they need to be dressed with some sort of smeared vortices. So one can write down the expression, but there's certain disorder operators in the bulk that are fermionic. Okay, so that's the basic two-dimensional story. I think it makes lots of things much clearer. In particular, it tells you immediately why in gauged and ungauged quantum mechanics there are canonical module structures, because over here the modules live on the other boundary conditions. It also tells you how to go back and forth. So if we want to ungauge quantum mechanics on X, we should start with the gauge theory, an NX strip, and produce the ungauged theory, a DX strip. The way to do that is by choosing an element of Ham and D. In cohomology, Ham and D, G equivariant cohomology of point times G is G equivariant cohomology of G, which as a vector space is trivial. There's a single element sitting there. There's absolutely no choice to be made about what local operator sits there. It's the generator of this C, sort of a 1. On the other hand, we can use this computation to figure out what to do at the chain level to ungauge the Hilbert space. The prescription by passing through this strip is to take G equivariant cohomology of X, tensor it, roughly speaking, with G equivariant cohomology of G, but that's you don't want to just tensor with C. You want to tensor with the resolution of C, and the way to actually do that is to tensor with the entire complex. Tensoring with, maybe write it like this, with the equivariant, the Cartan model of the equivariant de Rham complex does the trick. And one tensors over the C of sigma algebra. And so computing cohomology of this by standard manipulations is just the cohomology of X. And it produces more directly, it produces the G equivariant cohomology of X times G, which is just the cohomology of X. In equivariantly formal cases, this looks really stupid. This whole manipulation and this whole manipulation just boils down to setting the equivariant parameter to 0. And in most physics examples I've encountered so far, it is an equivariantly formal situation. You can just do this. But the whole point of this talk and yesterday's was that not all situations are equivariantly formal, and you have to go through some extra yoga. So that's ungaging. A cool thing to do would be to lift this systematically to higher dimensions. I can see bits and pieces working, and it is possible to sort of formalize what you would need for the story to work in higher dimensions, and the basic ingredients are all there, but I think there's a bit of hard work to do, especially at the categorical level, to get the equivalent, to get the analogs of these algebras. So in higher dimensions, you want to talk about categories of line operators and so on stuck to the boundary that are going to be acting. Telemann did a version of this a few years ago that he talked about in his ICM address. In fact, he was the first person to identify generally the Coulomb branch of 3D pure gauge theory, of 3D n equals square pure gauge theory. And he used that to understand G actions in Fukaya categories, in particular global G actions in Fukaya categories, engaging and ungaging. I think there's still quite a bit to do there and quite a bit to say in the physics. Yes? Yeah. Well, so the Yeah, so what one wants to do, I mean, just in pictures, you take pure 3D n equals 4 G-gauge theory with the Coulomb type twist, or the A-type twist. Which should look like the Rosansky-Witten twist on its smooth Coulomb branch. And so by understanding the complex symplectic geometry of the smooth Coulomb branch, one can start to play this game. Because the structure of the two category of boundary conditions in Rosansky-Witten theory was described quite explicitly by Kapustin, Rosansky, Salina. The boundary conditions for this are 2, 2, they're two-dimensional 2, 2, A-twisted theories, no longer pure gauge theories. They're just any theories with a Kähler target and G symmetry. Saying this at the categorical level, one sort of equates A-twists of two-dimensional theories with the Fukaya category. There's a sort of a cobordism hypothesis sitting in there, that the whole theory is determined by its category of boundary conditions. But one thing this should tell you by starting to work with corners, probably, it should tell you how to gauge and ungauge G symmetries in Fukaya categories. There's similar constructions that you see versions of this Neumann-Dirichlet picture all over the place. There's similar constructions that happened in geometric Langlands, and in the initial Kapustin-Witten paper, and then many of the subsequent ones on the topic. Exactly. Yes, absolutely. I should, looking at the time, I should say there's one very important thing to watch out for. Anomalies can destroy this construction. So in 3D n equals 4, there are no, in 2D 2, 2, there are no anomalies for G flavor symmetries. You can get anomalies for the R symmetry. However, if we don't use as much supersymmetry, if we were to try to play this game with, say, 3D n equals 2 and 0, 2 boundary conditions, as in Sergei and Abhijit's talks, now anomalies do get in the way. The fact that there's no topological twist is not such a problem. The only direction that actually needs to be topological is the transverse one, which you can obtain, but non-abelian G symmetries have anomalies. So there's an abelian version of this game that works just fine, but you use non-abelian groups. Yes. The problem is, yeah, exactly. You have to be much more careful. And in particular, pure gauge theory doesn't have a Neumann boundary condition because it's anomalous. Okay. Yes, exactly, you would. Yes, then you get the usual WCW picture. Okay, so when did I start? Oh, really? I have a whole 9 minutes left. Great. Awesome. So let me say some very quick things about 3D n equals 4. Okay, so yeah, first I should say this is based on a bunch of work, a lot of it with Gayoto and Matt Ballimore, Justin Hilburn, in part with Heechul Kim, and upcoming work with my student, Nick Garner, my first student, and a postdoc at Davis, Mike Gerasi, and Justin. It is also going to try to connect. In fact, one of my goals in this is sort of a bit of review connecting to the Braverman-Finkelberg-Nakajima construction of Coulomb branches. The data of a 3D n equals 4 gauge G, well, 3D n equals 4 gauge theory. So I talked about sigma models in Rosansky-Witten before, but now we want gauge theories with linear matter. And the data is a gauge group G and a quaternionic representation of G. Which, for anything computable, needs to take the form R plus R dual, where R is a unitary. Representation. In other words, T star R. So this is gauge group, this is the matter. One certainly should. It's been a big puzzle. It's been puzzling how to compute anything. The problem is that the computations I'm going to tell you about, at least most of them, require introducing boundary conditions. And it's hard to find boundary conditions, to come to boundary conditions for a half hyper. One needs G invariant Lagrangians inside R plus R dual for boundary conditions, or inside whatever the quaternionic map is. Anyway, that's sorry. I should actually really point that out as a genuine puzzle. Nobody knows how to include general quaternionic matter yet. So the moduli space of vacua of this theory contains at least two branches. The so-called Higgs and Coulomb branches, they're both hyperkähler. And in particular, in a fixed complex structure, they will look like complex symplectic manifolds. Now, in parallel with this, there are also two topological twists. QH and QC. In other words, two nilpotent supercharges with all of the properties that I wrote down 2 days ago. There are two topological twists with the property that the ring of functions, the algebra of topological operators in the H twist is holomorphic functions on the Higgs branch. And the algebra topological operators in the C twist is holomorphic functions on the Coulomb branch. in fixed complex structures, which go, these are choices to be made that go into defining QH and QC. The Higgs branch is easy to describe in terms of this data. It's the hyperkähler quotient of R plus R dual mod G, and as everywhere in these lectures, G is a compact Lie group. So it's a hyperkähler quotient, or in complex language, you might want to think of that as a symplectic quotient, as a holomorphic symplectic quotient of T star R by GC. What about the Coulomb branch? I can tell you very explicitly what it is quickly in one case, namely in pure abelian gauge theory, where R is 0. So here the Coulomb branch is C times C star. And that still contains some interesting information. The functions come from these complex adjoint valued scalars that exist in gauge theories in all of these dimensions. The functions on C star come from what are called monopole operators. And when I say functions come from operators, literally mean in the sense that that a topological algebra of local operators corresponds to functions on the moduli space. So these are the functions on C star are monopole operators, which are they're disorder operators defined by specifying some singularity in the gauge fields at a point. They're the 3D version of 't Hooft lines. What you get by compactifying an 't Hooft line on a circle. Right. So in this case, the topological algebra is generated by sigma v plus minus with the relation v plus v minus equals 1. And there's a symplectic form d sigma wedge d log v plus, and there's a deformation quantization. There has to be deformation quantization because that's how 3D topological theories behave. So the deformation quantization has the same generators. And a quantization parameter epsilon, where now sigma measures the monopole charge of these monopole operators, and the monopole operators don't do anything interesting. So it's a silly algebra. It contains raising and lowering operators that commute with each other. Yes. Yeah, that comes in a really stupid way from quantizing that symplectic form. Sorry? Oh, yeah, that's true. Yes, that's part of... Yes. In the abelian case, you can express everything in terms of dual photons. But I'm not going to. I'm going to try to say something quickly, and then maybe take questions. So, yeah, let me give you a philosophical story. So for general group and representation, the one very concrete thing that can be said about the Coulomb branch is that it's just like Hitchin systems for 4D theories. It's an integrable system over T mod W, the Hitchin base, where the fibers, the generic fibers, are complex dual tori of the group G. The fibers degenerate in various ways. They blow up along the discriminant locus, root hyperplanes. And they shrink along weight hyperplanes. I mean, weights of the representation are in the base. The thing is that that's really all anyone was able to say for a long time. Aside from a few isolated classes of examples, there was no general construction in physics of this space as certainly not as a hyperkähler space. And I think what happened is that discussing it as a hyperkähler space was so hard that people didn't really think to check how to, if there was an easier way to describe it as a complex symplectic space. Realizing that the ring of functions is actually a topological ring immediately tells you that there's a that the ring of functions can't be renormalized. And so another one of the reasons physically why the Coulomb branch is really hard to describe is that it gets serious non-perturbative quantum corrections. So you can't just do a classical computation. You have to take into account smooth monopole corrections to the metric, which people did with a lot of hard work in cases. So anyway, the fact that the ring of complex functions on this space is topological means that can't be renormalized. That doesn't get quantum corrections. Moreover, we now know, using the secondary product, that the symplectic structure on this space is also a topological property, and that can't get renormalized. The quantization is a topological property, and that doesn't get corrections either. So all of these things are actually not that bad to compute if you do them in a TQFT setting. So with Matt and Davide, we worked with operator algebras and actually proved non-renormalization theorems without realizing this topological thing, and then gave some algebraic description of the Coulomb branch. And then Braverman, Finkelberg, Nakajima looked at Hilbert series for the chiral ring and sort of guessed an amazing mathematical formula. That mathematical formula comes directly from a TQFT analysis, which I would tell you about, but I am also out of time. It's local operators in a topological twist. I mean, yes, but that's sort of like the next 10 minutes, and So we can just chat about it at lunch.
Still be normalized, right? By some boring phase, like total scale to some power. Can you see this?
Yes, they aren't. So there's a mild one loop correction that goes in, which is sort of saying you can't turn the gauge coupling completely off. And beyond that, there's nothing. It's slightly more subtle. Also, of course, there could be some extra instanton corrections, but there aren't to products. Like in the A model, you get quantum cohomology from instanton effects, and those can't happen here.
Also, in this picture, have you assumed that G is simply connected?
No.
So it's always weight hyperplanes, as opposed to hyperplanes given by the character lattice.
No, I mean it's weights of the representation, and whether it's no matter what the group is, like these are genuine.
I see.
Yeah.
So here, in this part, you're using both the topological twist and the omega deformation? I got a bit confused.
Topological twist here, omega deformation on top of it here.
So unlike in 4D n equal to 2, where these are sort of not compatible with each other, right? Like you either do the Donaldson type twist or you do the omega deformation. So is it different in 3D n equal to 4?
No, I think it's the same one. Omega deformation is a sort of a further deformation of the Donaldson twist. It acts a bit differently in 4D. This is more akin to Nekrasov-Shatashvili, where you just deform a single plane.
Would it be meaningful to act on the dx and nx strings with, say, xx strings, with x boundary conditions on both sides? Would that be meaningful?
Oh, I mean, you certainly can. It gives you the endomorphism algebra of x. Right? So that's the same thing as asking what are local operators between x and x. And so it's actually an interesting thing. It's not just a vector space, but an algebra. So what you find is equivariant cohomology of x times x, which is an algebra under convolution.
Shouldn't it be some kind of Floer cohomology?
No, it's in general yes, but it's too simple here.
Any other questions? Okay, if not, we'll thank Tudor again.